Right now, the farthest human-made object in existence is a spacecraft roughly the size of a small car, drifting through the thin darkness beyond our solar system. Voyager 1 was launched from the Kennedy Space Center on September 5, 1977. Its original mission was to study the giants of our own neighborhood, Jupiter and Saturn. It completed that task decades ago. Since its final flyby of Saturn in 1980, Voyager 1 has been traveling through interstellar space at a steady, unrelenting speed. It moves at approximately 17 kilometers per second, roughly 38,000 miles per hour. That is fast enough to cross the entire United States from coast to coast in under 4 minutes. It is fast enough to circle the entire Earth in roughly 40 minutes. Yet at this staggering speed, reaching the nearest star would take roughly 75,000 years. 75,000 years ago, modern humans shared this planet with Neanderthals. The entire history of our civilization, the invention of agriculture, the birth of writing, the rise and fall of every empire, and the dawn of the space age, fits comfortably inside the last 10,000 years. Voyager 1 would need more than 7 times the entire span of human history just to reach the front door of our closest neighbor. And that is only the first link in the chain. Tonight, we're going to confront the most humbling reality of our species. We've been taught that reaching the stars is only a matter of time and technology. We imagine that if we can just build better rockets, we will eventually claim the galaxy. But the universe did not place a single wall between us and the stars. It built a chain of them. Distance, energy, radiation, time, biology, and the fundamental laws of physics. Each one is linked to the next, so that solving any single problem only makes another one worse. By the end of this journey, you're going to understand why the distance between stars is not an engineering hurdle. It is the architecture of our isolation. Every civilization that has ever looked at the night sky has asked the same question. What is out there? The Polynesians crossed the vast Pacific Ocean using nothing but the rising and setting points of specific stars. The ancient Greeks imagined celestial spheres carrying points of fire across a dome of darkness. Aboriginal Australians read the dark spaces between the stars, building stories from the shape of absence itself. Every culture on every continent felt the same pull. The stars were calling, and humanity wanted to answer. Modern science inherited this ancient longing and added something dangerous to it: precision. We learned to measure the gaps. We calculated the energy. And the numbers that came back from that precision were not merely large. They were a different kind of large. A kind of large that breaks the relationship between what we want and what is possible. The dream of reaching another star is not a fantasy born from ignorance. It is a desire that grows stronger the more we understand. Astronomers have now confirmed the existence of over 5,000 exoplanets. We know for a fact that the targets exist. Telescopes like the James Webb are beginning to examine the atmospheres of some of the most promising worlds, searching for chemical clues that could reveal whether life is possible beyond Earth. We know of systems like TRAPPIST-1, roughly 40 light-years away, containing 7 Earth-sized worlds orbiting within or near their star's habitable zone. We can see the shores of other worlds, and yet we are the same generation discovering exactly how hostile the ocean is that separates us from them. To understand this hostility, we must look at where Voyager 1 stands today. Later in 2026, Voyager 1 is expected to reach a remarkable milestone: 1 full light day from Earth. This means that a radio signal traveling at the speed of light, the fastest anything can move in this universe, will take 24 hours to reach the spacecraft. Send a command in the morning, and you must wait all day and all night for the response to arrive the following morning. A full day for light itself to bridge the gap. Voyager 1 has been flying for half a century to cover this single light day. And yet our closest stellar neighbor, Proxima Centauri, is not 1 light day away. It is more than 1,500 light days away. Voyager 1 has crossed less than 1/1500th of the distance to the closest star. Human intuition fails here. Our brains evolved to process distances a body can walk or a hunter can scan. We have no biological framework for interstellar scale, so let us make it tangible. Imagine shrinking our entire solar system so that the sun becomes a basketball sitting on a sidewalk in New York City. At this scale, the Earth is a single grain of sand orbiting 26 meters away. Jupiter is a marble a block and a half down the street. Neptune, the outermost major planet, is a small pea half a mile from the Sun. Voyager 1, after 50 years of flight, has only traveled about 2 miles past that pea. It is still in Manhattan. Now look for the nearest star. At this same scale, Proxima Centauri would be another basketball sitting on a sidewalk in Honolulu, Hawaii, over 4,000 miles of absolute nothingness away. No waypoints, no landmarks, just a void that challenges the very meaning of the word emptiness. The interstellar medium is extraordinarily thin, far thinner than the best practical vacuums we can maintain over large volumes on Earth. It averages roughly 1 hydrogen atom per cubic centimeter. Compare that to the air you are breathing right now, which contains 25 quintillion molecules in that same space. But here is why this emptiness is a deception. Interplanetary travel and interstellar travel are fundamentally different categories of existence. Within the solar system, we can maintain a relationship with our machines. When a Mars rover has a software glitch, engineers can send a correction and wait minutes for the signal to arrive. But when a spacecraft is 4 light-years away, the same round trip takes more than 8 years. By then, the mission is not just over, it is ancient history. Communication delay severs the umbilical cord of humanity. You aren't being guided, you're being informed slowly about where you used to be. This realization forces the first choice of the chain. If slow travel means tens of thousands of years, then we must go fast. We must reach for 10, 20, or 50% of the speed of light. If we can reach 10% of light speed, that 75,000-year sentence shrinks to roughly 42 years of cruise time. It becomes a single human career. It makes the stars feel like a destination again. But this is where Einstein's relativity changes the equation. Speed is not free. As velocity approaches the speed of light, the energy required rises without bound. Every additional fraction of light speed becomes dramatically more expensive. No spacecraft capable of carrying humans has ever come remotely close to even 1% of light speed. You have solved the distance problem, but in doing so, you have awakened a much harder one: energy. Even if we pay the energy debt, the universe has another weapon hidden in the emptiness. At relativistic speeds, even the almost empty space between suns stops looking empty. Individual atoms and microscopic grains of dust become high-energy impacts, turning the interstellar medium itself into a radiation and shielding problem of extraordinary scale. At those speeds, even a tiny grain of dust can carry enough kinetic energy to produce a catastrophic impact. You are no longer crossing a void. You're being sandblasted by a galaxy. This is the transition from the distance barrier to the speed barrier. We thought the problem was how to get there. But we are about to discover that the faster you go to solve the distance, the more violently the universe tries to destroy you. The chain of barriers is beginning to tighten. We have survived the realization of the 75,000-year sentence, but we are about to enter a realm where even nothingness becomes a weapon. In the next section, we are going to look at the speed barrier. We will explore the staggering energy debt of the future, and why the closer we get to the speed of light, the more the universe resists our presence. Are you ready to see why going fast might be the most expensive mistake a civilization can ever make? Speed is the most seductive lie we tell ourselves about the cosmos. In our stories and our cinema, we treat velocity as a triumph, a heroic number on a digital display that brings us closer to our dreams. We imagine that if we can only go fast enough, we can shrink the universe, bridge the impossible gaps, and make the galaxy our own. But as we transition from the barrier of distance to the reality of the journey, we hit a wall that is not made of miles, but of the very fabric of existence. This is the speed barrier. We are about to discover that speed is not just a measurement of motion, it is a trade. You do not conquer the stars, you buy them. And the currency you use is energy, a currency that the universe has priced so high that even the combined output of our entire civilization may not be enough to afford the ticket. To understand why speed is a trap, we must first confront the intuition of the flat road. On Earth, our everyday experience tells us that if you want to double your speed, you simply apply twice the force or burn twice the fuel. This is the world of classical physics, where motion feels linear and predictable. But as you push toward the scale of the stars, the universe stops behaving like a flat road and starts behaving like a vertical cliff. Einstein's theory of special relativity, confirmed by more than a century of experimental evidence, describes what actually happens when you reach for the light. As an object accelerates, the energy required to push it even slightly faster does not grow in a straight line. At relativistic speeds, kinetic energy becomes an enormous fraction of the energy budget, and the more dramatically the energy cost rises, as relativity makes further acceleration increasingly expensive. The closer you get to light speed, the more violently the physics of the vacuum push back against your ambition. Think about the sheer energy debt of a relativistic crossing. In everyday life, kinetic energy is a manageable number, but at the speeds required for interstellar travel, the math enters a different realm. Consider a modest spacecraft massing 10,000 kilograms, roughly the weight of a large commercial truck. To accelerate that single truck to just 10% of the speed of light would require a kinetic energy of approximately 45 quintillion joules. To our human minds, that number is an abstraction, so let us give it a name. That is roughly the energy released by more than 1,000 megatons of TNT. For context, that is more than 20 times the yield of the Tsar Bomba, the most powerful nuclear device ever detonated. Accelerating a single truck to 1/10 the speed of light requires the concentrated energy of a planetary-scale cataclysm, and a truck is not a starship. A vessel carrying humans, life support systems, shielding and fuel would mass hundreds of thousands of tons. We are talking about energy budgets that belong to stars, not to engines. This leads to the first what moment of the speed barrier, the realization that the energy required to reach the stars could dwarf the entire productivity of our world. In 2024, the total global energy consumption of all human civilization was roughly 600 quintillion joules. Even ignoring the inefficiency of real propulsion, accelerating just 10,000 kilograms to 90% of light speed would require energy comparable to roughly 2 years of humanity's present-day total energy consumption. And that assumes we could somehow convert all of that energy into the spacecraft's motion with perfect efficiency. In the reality of engineering, where heat is lost and engines fail, that cost could climb into the decades. This is the energy wall. It does not depend on how clever your engine is or what fuel you use. It is a fundamental tax imposed by the geometry of spacetime. But the energy requirement is only the entrance fee. To actually move that energy, you must face the tyranny of the rocket equation. Formalized by Konstantin Tsiolkovsky in 1903, the equation describes the fundamental relationship between a rocket's exhaust velocity and the amount of fuel it must carry. A rocket is a machine that must carry its own energy. As you burn fuel to produce thrust, you get lighter, but to get that fuel up to speed in the first place, you had to burn even more fuel. For chemical rockets, the workhorses of our age, the exhaust velocity is limited by the chemistry of fire. Using chemical propulsion, the required mass ratio becomes so extreme that the concept stops being remotely practical long before reaching even 1% of light speed. We aren't just limited by technology, we are limited by the energy density of the chemical bond. We look to nuclear fusion or antimatter as the potential saviors of the dream. Fusion, the process that powers the sun, could theoretically provide exhaust velocities hundreds of times higher than chemical rockets. But even with the most optimistic fusion designs, a ship trying to reach 10% of light speed would require a fuel mass thousands of times greater than the ship itself. The only fuel that truly breaks the tyranny of the rocket equation is antimatter, where matter meets its mirror image and converts its combined mass into pure energy. But antimatter is a ghost. Humanity has produced only microscopic quantities of antimatter, vastly less than what an interstellar spacecraft would require. The gap between our current capability and the requirements of the stars is measured in more than 20 orders of magnitude. It is the difference between a single drop of rain and the entire Pacific Ocean. While we struggle with the fuel, we are also ignoring the biological speed limit of the human body: acceleration. We imagine a starship jumping to warp speed in a heartbeat, but a human body is a fragile bag of fluid and bone. We can survive the 1G pull of Earth's gravity indefinitely, but we cannot survive the crushing forces of high-speed maneuvers. To reach 10% of the speed of light at a constant, comfortable 1G acceleration, the ship's engines must fire continuously for 35 days. To reach 77%, they must fire for an entire year. During that year, every second of thrust consumes fuel, and every kilogram of fuel consumed is a kilogram that had to be accelerated during the preceding seconds. The human body sets a medical ceiling on how fast we can speed up, and the rocket equation penalizes the long burns that ceiling requires. The two constraints squeeze the mission design from opposite sides until there is no room left for survival. This leads to the final, absolute wall, the speed of light itself. We often talk about light speed as a goal, but in the reality of physics, it is a boundary that can never be reached by anything with mass. As a massive object approaches 300,000 kilometers per second, the energy required to move it even slightly faster approaches infinity. This is not an engineering challenge, it is a structural feature of the universe. At the Large Hadron Collider, we accelerate protons to 99.9999% of the speed of light. At that velocity, a single proton carries enormous energy for something so small, and billions of such particles circulate inside the machine. Yet, even for these tiny particles, reaching exactly 100% would require infinite energy. The speed of light is the cage in which we are all contained. And yet, even at 99% of light speed, the universe remains staggeringly large. Proxima Centauri is still 4 years away. The center of our galaxy is still 26,000 years away. Speed does not solve the distance, it only changes our relationship to it. The faster we go, the more the universe begins to distort around us. At these velocities, the thin hydrogen gas between the stars becomes a lethal radiation storm. A single hydrogen atom striking your hull at 90% of light speed can carry hundreds of millions of electron volts of kinetic energy. At that speed, even the emptiness between stars becomes a stream of microscopic projectiles. The faster you go to save time, the more violently you are irradiated by the vacuum itself. You have solved the first wall of time by spending the wealth of a planet on energy, only to find that the very act of moving has turned the space between stars into a weapon. The speed barrier is not a single gate that we can unlock with a new discovery. It is a series of interconnected physical laws that ensure that the faster we reach for the stars, the more the universe pushes back. We have attempted to solve the distance with speed, but we have only succeeded in making the journey more lethal. In the next section, we are going to look at the warp barrier. We will discover why the most popular loophole in physics, the Alcubierre drive, is not the bridge we were promised. We will see why bending spacetime doesn't actually bypass the energy debt, and why a ship that cheats the speed of light might be the first vehicle in history that cannot be controlled from the inside. Are you ready to see why even if we fold the universe, the stars are still too far. When we look at the stars, we feel the weight of our own limitations. We have spent this journey climbing the ladder of cosmic barriers, from the crushing span of trillions of miles to the staggering energy debt required to bend reality. We have seen that the faster we try to run, the more violently the universe pushes back. It is a game designed for us to lose. But in the mid-1990s, a new hope emerged, a mathematical loophole that seemed to offer a way out of the cage. We call it warp drive. In our collective imagination, it is the ultimate cheat code, the technology that allows us to fold space, ignore the speed of light, and cross the galaxy without the penalty of time. We see it as a bridge, a way to make the impossible manageable. But as we transition from the dream of the engine to the reality of the geometry, we hit a wall that is not made of distance or energy, but of logic. This is the warp barrier. In this section, we are going to explore why the most popular solution in science fiction is actually a psychological and physical trap, and why the warp drive did not destroy the barrier, it simply moved it. To understand the warp barrier, we must first look at the man who identified the loophole. In 1994, a physicist named Miguel Alcubierre asked a question that no one had formally put to Einstein's equations before. What if instead of pushing a ship through space, we arranged for space itself to move? Alcubierre didn't ask how to build a faster engine, he asked how to move the ocean. His math proposed a bubble of space-time, contracting the universe in front of the ship and expanding it behind. The ship itself would sit in a pocket of absolute stillness, while the fabric of reality carried it forward. Because the bubble is not an object moving through space, but rather space itself in motion, the local light speed limit does not apply in the same way. In theory, the bubble could carry a ship to Proxima Centauri in weeks, days, or even hours. It promised us the galaxy without the time dilation or the g-forces. But the universe does not grant exceptions for free. The first major wall of the warp barrier is the energy sign. For decades, the Alcubierre drive was considered a mathematical ghost because of its requirement for negative energy density. In our world, all known matter and energy are positive. They have weight, they cause gravity to pull things together. But to expand spacetime behind a ship, the equations require a region where the energy density falls below the reference vacuum level, a state emptier than empty. We were trying to build a bridge to the stars using exotic matter that has never been observed in the macroscopic world. We were essentially trying to build a cathedral using shadows as bricks. Initial estimates were so extreme that they were often expressed in terms of planetary mass-energy scales, with some formulations reaching the equivalent of Jupiter. We had found a loophole, but the required energy had the wrong sign. And this is where the story takes its first turn. The warp drive had not destroyed the barrier, it had moved it into the realm of the exotic. But even if we assume we could pay the energy debt, we encounter a second wall that is built into the very logic of faster-than-light travel, the horizon problem. Imagine a ship encased in a superluminal warp bubble, racing toward a destination at twice the speed of light. Because the leading edge of the bubble is moving faster than light, any signal sent from the bridge toward the front of the ship can never reach its destination. The signal is made of light, and it is trying to catch a wall that is already outrunning it. You are shouting at a door that is moving away from you faster than your voice can travel. This is the first major realization of the horizon trap, the possibility that the interior of a warp bubble is causally disconnected from its own front door. In the simplest superluminal warp drive models, the crew cannot causally control the bubble's leading edge, making steering, and even safely shutting the system down from inside, theoretically problematic. You are no longer a pilot. You are a passenger in a high-tech coffin, watching the digital displays of a ship that has outrun its own ability to be controlled. You have built a bridge to the stars, but you have forgotten that a bridge only works if you can choose where to step off. And if the bubble's trajectory could not be modified from the inside, Even a microscopic navigation error introduced before departure could become enormous over interstellar distances. You arrive at the coordinates of a star, but the star is not there, and you have no way to turn back. But as the horizon problem appeared to settle into the mathematics, another barrier emerged from the space around the bubble. This is the possibility of particle accumulation, often called the snowplow effect. We think of interstellar space as a perfect vacuum, but it is actually filled with a thin soup of hydrogen atoms and dust. In some superluminal warp drive models, matter and radiation encountered along the path can become concentrated around the bubble's leading boundary, creating a potentially catastrophic accumulation of energy. The particles hitting the front of the bubble cannot move backward into the ship, and they cannot move forward because the bubble is outrunning them. If this happens, the bubble wouldn't simply be crossing the interstellar medium. It could be carrying a concentrated layer of that medium toward its destination. You are not just transporting a ship across space. You may be transporting the consequences of everything the bubble encountered along the way. You are essentially building a cosmic shotgun as you travel, and the faster you go, the more dangerous the cargo becomes. In the most dangerous versions of this scenario, the accumulated energy could be released toward the destination at the moment the bubble collapses. Your arrival might not look like a landing, it could look like an astronomical weapon switching on. The civilization waiting for you might never see the ship itself. It might see only the focused burst of high-energy radiation the ship carried in front of it. Your first step into a new solar system could become the act that destroys it. This realization flips the narrative of the Starship Pioneer. We imagine ourselves as explorers bringing the light of humanity to the dark, but the physics of some warp bubbles suggests that if we want to cross the distance quickly, we might pay for it by arriving as a catastrophe. It suggests that the loophole Miguel Alcubierre found was not a gift. It was a reminder that some boundaries are meant to stay closed. This is why the 2024 breakthroughs in warp physics are so revealing. Researchers recently proposed theoretical warp drive configurations that use ordinary positive energy while remaining strictly subliminal. The breakthrough was important. It proved that warp spacetimes are real physical possibilities that don't require exotic matter, but it came with a devastating limitation. We had improved the physics of the drive, only to lose the one feature we wanted most, the ability to outrun light. The warp barrier has won, not by breaking your engines, but by breaking your intent. We have built a ship that can bend the universe, but we have found that the universe is not a passive medium. It is an active participant in our journey, and it has a way of turning our speed into a liability. We have surrendered the slow, manageable journey of the rocket for a high-speed, autonomous exile. We have survived the initial mirage of the drive and the energy debt required to power it, but we are losing the battle of control. We are the first generation to realize that the most dangerous thing about FTL travel isn't the vacuum, it's the loss of the steering wheel and the birth of the cosmic weapon. And now the story gets worse, because even if we abandon faster-than-light travel and accept a physically allowed controllable subliminal warp drive, the universe still has one weapon left, the space between stars. Because even if we move slower than light, we cannot move without touching the medium. And at 90% of light speed, even nothingness becomes something. A single grain of dust stops being dust. It becomes a weapon. In the next section, we enter the radiation barrier, and the realization that the vacuum between the stars is actually the most dangerous substance in the universe. Are you ready to see why on a starship, the most lethal enemy is a single atom? We have spent our history defining a vacuum as the absence of everything. We look at the space between stars and see a perfect, unyielding nothingness, a silent hallway that offers no resistance and hides no traps. We assume that if we can build a ship that bends space, or an engine that reaches relativistic speeds, we can simply slide through this void like a needle through silk. But as we move from the cost of the engine to the reality of the crossing, the most fundamental assumption of spaceflight begins to shatter. You are about to discover that in the interstellar medium, nothing is a lie. At near light speeds, the vacuum doesn't behave like an empty room, it behaves like a solid wall. This is the radiation barrier. In this section, we are going to explore why the space between stars is actually the most dangerous substance in the universe, and why traveling at the speed of your dreams turns the very fabric of the galaxy into a weapon of mass destruction. To understand the horror of the crossing, we must first confront the density trap. On Earth, we are protected by a thick, heavy atmosphere. The air you are breathing right now contains roughly 25 quintillion molecules in every cubic centimeter. Interstellar space, by comparison, is incredibly sparse, containing on average only one single hydrogen atom per cubic centimeter. To our human intuition, this sounds like a frictionless paradise. But as you push your starship toward 90% of the speed of light, the math transforms the story. At those speeds, even a modestly sized ship would encounter trillions upon trillions of hydrogen atoms over every second of flight. Over a journey of 25 trillion miles to the nearest star, your ship is not passing through a void. It is colliding with a landslide of matter. You are no longer a ship in a vacuum. You are a high-speed projectile moving through a cloud of invisible, high-energy bullets. This leads to the first major realization of the radiation barrier. At relativistic speeds, mass is replaced by kinetic energy. In our everyday world, a grain of dust is a nuisance, something you wipe off a shelf, but kinetic energy increases with the square of velocity. As your ship approaches the speed of light, the energy carried by even the smallest particle becomes catastrophic. Imagine a single microscopic grain of dust, weighing less than a milligram. Striking your ship at a significant fraction of light speed, that grain carries enough kinetic energy to produce a catastrophic impact. You aren't just traveling through space, you're being sandblasted by a hail of relativistic impacts. The interstellar medium, which felt like a ghost when we were planning the mission, has now developed teeth. It is actively trying to dismantle your hull, atom by atom, second by second. Think about the shielding paradox. To survive this bombardment, we imagine our starships encased in massive armor, meters of lead, or sophisticated electromagnetic deflectors. But in the reality of relativistic physics, armor is a double-edged sword. When high-energy particles strike a massive shield at relativistic speeds, they can trigger nuclear fragmentation and particle cascades, producing secondary neutrons, gamma rays, and other radiation inside the shielding itself. The very material you built to protect the crew can become part of the radiation problem. The more armor you add, the more shrapnel you create at the nuclear level. You are trapped in a biological cage, huddling behind a wall that is being turned into a radiation source by the very space it is trying to cross. You are being attacked by your own ship. The impact on human biology is not a sudden explosion, but a slow, quiet molecular erasure. Even if your hull remains intact, it cannot stop the high-energy heavy ions that treat solid matter like tissue paper. These are galactic cosmic rays, particles accelerated by distant supernovae that have been racing through the void for millions of years. On Earth, our atmosphere shatters these ions before they can touch us, but in deep space, they arrive with their full destructive power. They can damage DNA, increase cancer risk, and injure healthy tissue. Crucially, they may affect the nervous system in ways we still do not fully understand. The pioneer doesn't just have to survive the journey, he has to arrive with the same brain that began it. In the deep dark, your own biology becomes a clock that is being methodically unwound by the stars. This mechanical and biological siege is compounded by the thermal execution. We think of space as cold, and at 3 degrees above absolute zero, it is. But a relativistic ship is a machine of extreme energy. Every collision with interstellar matter deposits energy into the spacecraft. Every reactor pulse produces waste heat, and every joule that cannot escape eventually becomes a thermal problem. In a vacuum, there is no air to carry that heat away. The ship can only cool itself through radiation, a painfully slow and inefficient process. As you race toward the stars, the ship's hull begins to glow with infrared heat. You aren't freezing in the dark, you are being cooked inside a high-tech thermos. The faster you go to save time, the more energy you generate, and the more the universe refuses to let you cool down. But the real terror of the radiation barrier is the information horizon. As the ship moves deeper into the void, the light ahead becomes strongly blue-shifted, pushing some incoming radiation toward much higher energies. The stars ahead are no longer just destinations, they become part of the radiation environment. The sky in your cockpit window is no longer a collection of familiar yellow suns. It is a distorted, blinding tunnel of high-energy light. You are flying through a sky that is physically trying to bleach you. Meanwhile, the sun behind you is red-shifting, fading into an infrared ember. You are becoming a citizen of the between, severed from the light of your home and blinded by the light of your destination. The stars have stopped being landmarks and have started being hazards. And then there is the particle beam effect. By moving at near light speed, your ship is essentially turning the interstellar medium into a particle accelerator beam aimed directly at itself. Each individual hydrogen atom can carry roughly a gigaelectronvolt of kinetic energy at 90% of light speed. The particle flux is sparse, but every impact can trigger a cascade of secondary particles inside the spacecraft. This is the friction of reality. The radiation barrier suggests that the universe has a security protocol built into its distances. It allows us to dream of the stars, but it punishes the attempt to reach them quickly. If we stay below the speed of light, we are claimed by time. If we try to bypass the light, we are claimed by the environment. This is the ultimate dilemma of the interstellar traveler. We have survived the initial mirage of the drive and the energy debt required to power it, but we are losing the battle of the crossing. We are the first generation to realize that the most dangerous thing about an interstellar ship isn't that it might fail. It's that the very act of moving turns nothing into a weapon. We have built a machine that can bend space, only to find that space is ready to break the machine. But as the hull thins and the radiation rises, we are still ignoring the most silent assassin of all. We think that if we can just solve the shielding, if we can just find a way to bleed the heat and deflect the atoms, we will survive. But the human mind is not built for the between. It is a planetary organ that requires a horizon to stay sane. In our desperate attempt to cross the void, we are forgetting that the ship is not just a vehicle, it is a cage of time. In the next section, we are going to look at the time barrier. We will explore the time dilation paradox, the horror of outliving your own world, and why the first person to reach the stars might return to find an Earth that has already forgotten their name. Are you ready to see why in the deep dark, your own watch is the most lethal enemy you possess? We are a species built on the rhythm of a shared now. In everyday life, we behave as if a second is a second everywhere. We treat the present as something the entire planet shares, a universal constant that binds our history, our laws, and our relationships into a single, coherent story. Whether you are in London, Tokyo, or a remote island in the Pacific, we assume that if it is noon for us, it is noon for everyone else at that exact moment. This perception of absolute simultaneity is the foundation of our sanity. It allows us to believe that no matter how far we wander, we are still part of the same timeline as the people we love. But as a starship accelerates into the relativistic regime, this foundation doesn't just crack, it vanishes. You are about to discover that speed is not just a measurement of motion, it is a trade. You do not conquer the stars, you buy them, and the currency you use is time. This is the time barrier. In this section, we are going to explore why the faster you travel to find your way home, the further that home drifts into a future that no longer recognizes your name. To understand the horror of the clock, we must first look at the broken simultaneity of the universe. Einstein's theory of special relativity reveals that time is not a universal river. It is a personal experience woven into the fabric of your own movement. The faster you move through space, the slower you move through time relative to those you left behind. On Earth, we are blind to this reality because our fastest machines move at a microscopic fraction of the speed of light. To us, the now feels absolute. But for a pioneer attempting to bridge the light years, time dilation is no longer a mathematical ghost. It is a physical blade that methodically severs their connection to the human species. Imagine you are the pilot of a ship traveling at 99% of the speed of light. To you, inside the hull, everything feels normal. You eat, you sleep, you breathe at the same pace you always have. Your ship's atomic clock ticks with perfect clinical regularity, but the universe is performing a quiet surgery on your life. Because of your velocity, your now has decoupled from the now of Earth. At 99% of light speed, every year you experience corresponds to more than 7 years passing on Earth. This is the first wait. What? Moment of the relativistic journey. You aren't just traveling through space, you are traveling through the future of your own species. You are a man in a bubble of slow time, watching through a digital pinhole as the world you love accelerates toward its end. This leads to the postcard from the grave effect, the emotional cost of the relativistic trade. Imagine that during your journey, messages from Earth begin arriving from a world that is aging years or decades faster than you are. Because of the combination of light travel delay and time dilation, the cadence of your life story begins to warp. One message tells you your daughter has married. Another, arriving only months later in your timeline, tells you she has had a child. And eventually, a message arrives from a world where everyone you remember as young is now old or gone. You are grieving people whose entire lives are unfolding while only months or years pass for you. You are a biological relic, a mind inhabiting a future that was never meant for you. You aren't just far from home, you are later than home. There are two separate anchors pulling you away from Earth, and both are absolute. The first is the simple delay of light. Even at the nearest star, 4 light years away, a conversation takes nearly 9 years to complete. The second is time dilation itself, the physical stretching of your existence. Together, they create a temporal exile. Every relativistic journey creates a growing mismatch between the time you experience and the history unfolding behind you. You return to a world that has treated you as a historical footnote for a century. You are the hero who returned to find that the very civilization that sent you has already moved past the reason for your mission. This is where the warp drive was supposed to be our salvation. In Miguel Alcubierre's original mathematical formulation, the ship sits inside a region of nearly flat spacetime, while the geometry around that region contracts ahead and expands behind. The idea was seductive: move the geometry, not the ship, and potentially avoid the most extreme effects of time dilation. But as we have explored, the faster-than-light path is blocked by the horizon trap and the radiation execution. To survive the journey, we are forced to stay below the light speed barrier, and in the subliminal world, the trade for time remains. Even if we can lower the dilation through clever geometry, we cannot escape the arrival mismatch. The psychological toll of this fast-forward history is a slow-motion execution of the spirit. Species that is separated by decades of time dilation is no longer a single civilization. It is a collection of isolated islands. If the refresh rate of a single human thought is a decade, how can there be a shared culture? The time barrier severs the mission from the civilization that launched it. You start to identify more with the eternal now of the vacuum than the fleeting then of the planet. You realize that you aren't a pioneer. You're a piece of data that was never meant to be read twice. The clock has won, not by stopping your heart, but by making your heart irrelevant to the rest of the world. We have survived the distance barrier, the speed barrier, and the radiation barrier, but we are losing the battle for context. We are the first generation to realize that the most dangerous thing about the stars isn't that they are far, it's that they are future. We have attempted to solve the distance with speed, but we have only succeeded in making ourselves ghosts. We arrive in a future that has no room for our past, carrying the memories of a world that has long since evolved beyond them. But time is not the only thing your body has to survive. Even if the traveler accepts becoming a stranger to Earth, the human organism itself begins to change long before the journey is over. Bones weaken, muscles disappear, vision changes. The cardiovascular system adapts to a world without weight, and radiation continues its invisible attack at the cellular level. We think that if we can just solve the physics, we will succeed, but we are ignoring the fact that our bodies were never designed for the between. In the next section, we are going to look at the biological barrier. We will explore the silent dismantling of the human frame and why the most lethal enemy in the deep dark is the very biology that allows you to breathe. Are you ready to see why your own skeleton is the first thing that will betray you? On Earth, we are the beneficiaries of an open system. We live with the assumption that the world around us is a self-healing, self-regulating engine of abundance. If a building crumbles, we have the materials of a planet to rebuild it. If a crop fails, we have a global trade network to replace it. We have never had to live in a world where every critical resource must be accounted for, and where the loss of a single specialized skill is a sentence of extinction. But as we transition from the fragility of the human body to the cold logic of the machine, we hit a wall that no amount of engineering has ever breached. This is the self-sustaining barrier. We are about to discover why a starship is not a vehicle at all, but a fragile island of order drifting through an ocean of entropy. We will see why the greatest threat to a 100-year voyage isn't a lack of fuel, but the terrifying reality that in total isolation, both machines and civilizations eventually lose the will to function. To understand the horror of the machine, we must first look at the parasitic outpost. On Earth, we celebrate the International Space Station as a triumph of human persistence. It has hosted human beings continuously for decades, and we use it as a blueprint for our future among the stars. But the station is not a starship. It is a parasite. It is tethered to Earth by a continuous umbilical cord of resupply. Every few months, a vessel arrives carrying fresh water, new oxygen canisters, spare electronics, and specialized tools. Behind the crew stands a literal army of thousands of engineers on the ground, monitoring every breath of the station in real time. Without that continuous support from Earth, the station's long-term survival would eventually become impossible. An interstellar mission has no mother world to call upon. The moment the engines fire, the umbilical cord is not just stretched, it is severed. Every space mission in our history has depended on an open-loop system. We take what we need from Earth and discard what we don't. But on a century-long journey, every critical resource you carry at launch is the total inventory for the duration of the mission. You must achieve what no civilization in history has demonstrated, a perfect 100% closed loop. In the late 1980s, humanity attempted to model this kind of closure with Biosphere 2. It was a 3-acre sealed ecosystem in Arizona designed to support 8 people. But within 2 years, its oxygen levels had fallen dramatically, its ecology had become unstable, and the experiment had exposed just how difficult it was to reproduce Earth's self-regulating systems. We can build machines that scrub air and filter water, but we cannot easily replicate the billions of years of evolutionary tuning that keep a biosphere in equilibrium. A starship's life support system is not a garden. It is a high-tech resuscitation of a dying world, and every year the rhythm becomes harder to maintain. Even if the ecosystem remains stable, the mechanical entropy of the ship will eventually claim the mission. On Earth, we believe that strong means permanent, but in the reality of the deep dark, time is a solvent. Every moving part has a finite operational life. Bearings wear out, seals age, and electronic components suffer from electromigration, where electricity physically pushes atoms out of place, creating microscopic voids. Over a 100-year voyage, the ship will experience millions of thermal cycles, creating material fatigue that grows with every light year. The terrifying reality is not that a single processor might fail, but that the ship's very capability to replace it might go extinct. To keep a starship functional for a century, you don't just need spare parts. You need an entire industrial civilization capable of manufacturing them from scratch. You are in a race against the slow, quiet disintegration of your own world, and the universe is methodically dismantling the finish line. But as the metal tires, a much more profound decay begins to take hold inside the mind of the colony. A starship is not just a collection of wires, it is a collection of ideas. The systems that keep the crew alive, the reactors, the scrubbers, the navigation computers, are the products of thousands of years of accumulated human expertise. But knowledge is a living thing. It requires a culture to survive. History shows us that specialized knowledge can vanish in a few generations if the social structures supporting it are disrupted. After the fall of the Western Roman Empire, many of the sophisticated techniques behind Roman concrete and large-scale infrastructure were no longer practiced or understood. The aqueducts were still standing, the structures were still visible, but the people living in their shadow no longer knew the recipe to fix them. They had lost the language of their own technology. Imagine a generation ship in year 80 of its journey. The people currently in charge were born in the void. They have never seen an ocean or a factory. They have learned their engineering from manuals written by ancestors who have been dead for decades. This is the knowledge divorce. If a master engineer dies before their apprentice is fully trained, a tiny sliver of the ship's survival is lost. Over a century, these microlosses accumulate into a dark age of engineering. The crew might still know how to operate the ship, but they may no longer understand the fundamental physics required to innovate when an unexpected failure occurs. They become ritual technicians, performing the motions of maintenance without the depth of understanding. They are the residents of a high-tech haunted house, surrounded by machinery they can no longer truly control, praying that the machine mother doesn't stop breathing. This civilizational isolation creates a state of cultural stagnation. On Earth, we are part of a global conversation, constantly renewed by new ideas and unpredictable challenges. But on a starship, the library is finite. The conversations have all been had. When every resource is rationed and every role is predetermined by the ship's survival needs, the drive for creativity dies. You are building a society where change is a threat to the equilibrium. You have reached for the stars, but you have done so by turning humanity into a maintenance unit for a machine that has forgotten why it left home. The greatest distance on an interstellar voyage isn't the light years between suns, it is the gap between the people who launched the ship and the people who must finish the journey. This leads to the final, most haunting irony of the self-sustaining barrier, the arrival. We imagine that once the ship reaches another star, the struggle ends. But if you arrive at a world like Proxima b, a scorched, tidally locked rock, you are faced with an impossible choice. You cannot land because your body has been dismantled by the journey, as we saw in the previous chapters. You cannot return because your fuel is gone. Your only option is to continue living in the machine. But the machine is now a century old. Its seals are aging, its electronics are degrading, and the deep knowledge of its construction is a fading memory. The self-sustaining machine was never meant to be a permanent home. It was meant to be a bridge. And when the bridge doesn't lead to a shore, it becomes a cage. The self-sustaining barrier has won, not by a sudden explosion, but by the slow, relentless pressure of entropy. You have built a ship that can survive the radiation and the vacuum, but you have found that you cannot build a civilization that can survive time. You have traded the messy, dangerous, but self-healing world of Earth for a sterile, perfect, but terminal island. We are the first generation to realize that the most dangerous thing about interstellar travel isn't the distance. It's the fact that the universe does not provide a safe point. Once you leave the cradle, you are in a race against the decay of your own technology and the narrowing of your own mind. Because after everything we have tried, better engines, faster ships, artificial gravity, radiation shielding, and self-sustaining civilizations, we are finally approaching a barrier that cannot be repaired, out-engineered, or outgrown. It is written into the structure of reality itself. In the next section, we confront the physics barrier and the possibility that the universe has placed a hard limit on how much of itself any civilization can ever reach. There is a wall in the universe that no engine can burn through, no shield can absorb, and no civilization can negotiate with. It does not care how advanced we become. It does not care how much energy we possess. It does not even care whether we understand its nature. It is built into the most fundamental relationship between space, time, and causality itself. This is the physics barrier. Throughout this journey, we have seen how every solution has simply opened the door to a more terrifying problem. Faster engines created energy crises. Relativistic speeds created radiation storms. Long-duration journeys created biological collapse, and closed systems created mechanical and institutional decay. But beneath all of these technological hurdles, we have finally reached a threshold that cannot be out-engineered. We are about to discover that the universe may not be a connected whole, but a collection of isolated islands, partitioned by a logic that ensures every civilization remains a prisoner of its own coordinates. To understand the absolute finality of this wall, we must first look at the speed of light, not as a target, but as a boundary of logic. In our popular culture, we treat the number c, 299 million meters per second, as a speed limit, much like those on our highways. We imagine it is a record waiting to be broken by a sufficiently powerful machine. But in the language of physics, the speed of light is the speed of causality. It is the maximum rate at which one event in the cosmos can influence another. This is the first what moment of the final barriers. The speed of light is not a limitation of our current technology, it is the refresh rate of reality itself. The universe has a built-in delay, a latency that is hard-coded into the vacuum, ensuring that no piece of information can ever outrun the fabric that carries it. Most people understand the energy debt of approaching light speed, the fact that as you go faster, the energy required to accelerate further rises without bound. But the physics barrier reveals a much more disturbing reason why this limit is impenetrable. It isn't just about the power of your reactor, it is about the consistency of time. In the framework of special relativity, faster-than-light signaling would allow some observers to describe a signal as arriving before it was sent, effectively opening the door to violations of causality. If you can move information faster than light, you are no longer just moving through space. You are potentially moving out of the logical sequence of history. You are creating a universe where an effect could precede its own cause. This leads us to the chronology protection conjecture, a concept famously proposed by Stephen Hawking. It suggests that some unknown physical mechanism, perhaps a runaway quantum feedback loop in the vacuum itself, may prevent closed time-like curves from ever becoming physically realizable. The universe appears to protect its own timeline with a ferocity we are only beginning to comprehend. We aren't just looking for a faster engine, we are attempting to commit a logical crime against the structure of reality. And the evidence suggests that the laws of physics act as a cosmic immune system, shutting down any attempt to bypass the fundamental order of time. Think about the light cone, the geometric representation of everything that can ever influence your existence. Every star you can see and every event you can experience sits within this bubble. Beyond it lies the elsewhere, regions of the universe that are physically, causally, and permanently disconnected from you. For practical, civilization-scale travel, the reachable universe may be only a tiny fraction of the observable universe. We are witnessing a partitioned cosmos, a reality that has been broken into isolated cells. You are not a citizen of the galaxy. You are a resident of a light cone, and the laws of physics have ensured that you can never step outside its walls. This isolation is compounded by the terrifying reality of cosmic expansion. We live in a universe driven by the mysterious pressure of dark energy. This means that every second, the distance between us and the furthest galaxies is growing. But here is the mind-blown realization. Because cosmic expansion is accelerating, some sufficiently distant regions are already receding from us so rapidly that light emitted there today will never reach Earth. They have already slipped over the cosmic event horizon. Every day, more stars and more galaxies are crossing this line, vanishing from our future forever. We are living in a house where the rooms are moving away from each other so fast that we can only ever stay in the hallway. The universe is not a frontier for us to claim. It is a fading miracle that we are only allowed to watch as it retreats into the dark. The psychological toll of the physics barrier is a state of civilizational humility. On Earth, we have always believed that we could conquer any distance, but the laws of nature tell a different story. They suggest that an interstellar empire is a contradiction in terms. If it takes years for a message to travel between suns, there is no shared now. There is no collective intelligence. A species that spreads across the light years is a species that fragments into isolated, diverging pieces that eventually forget their common origin. The universe has set a causal lockdown on intelligence, ensuring that every civilization develops and dies in absolute clinical isolation. This provides the deepest possible connection to the Fermi paradox. We point our radio telescopes at the sky and wonder why the silence is so absolute. Perhaps it isn't because life is rare, or because civilizations are short-lived. Perhaps it is because every advanced intelligence eventually reaches the same mathematical conclusion: the door is locked. They look at the speed of light wall and the horizon of causality, and they realize that the resources required to fight the universe's own logic are better spent perfecting their own home. The silence of the stars might be the sound of a billion civilizations deciding that out was never an option. We are looking for neighbors in a universe where the laws of nature act as the ultimate social distancing protocol. But there is a final, most unsettling irony buried in the physics barrier. We often talk about the dream of the stars as if it were a future event, but physics tells us that the stars we see are not there. Because of the light delay, we are looking into a graveyard. Some of the brightest suns in the night sky may have already exploded or faded, but their ghosts are still traveling toward us. We are obsessed with reaching a reality that has already passed us by. We are like children chasing the image of a ship that sailed centuries ago, never realizing that the ship is already dust. The physics barrier has ensured that we can never truly arrive, because by the time we do, the destination we aimed for has already ceased to exist. One by one, every solution has opened a deeper problem. We solved the distance with speed, and speed gave us the energy wall. We solved the energy with the dream of warp drive, and warp drive gave us the horizon trap. We solved the journey with self-sustaining machines, and the machines gave us mechanical decay. And now, beneath all of them, we have reached the fundamental structure of the cosmos, a structure that refuses to hold still and refuses to let us through. The physics barrier is the final verdict of the universe, a reminder that we are not the masters of space-time, but its products. We are a planetary event, and the universe has ensured that we remain one. But as the realization of our isolation sets in, as we look up at the stars and see the walls of our cage, a new and much more profound question remains. If the barriers of physics are absolute, and the stars are logically unreachable, then what was the purpose of the dream? Why did we spend centuries building the telescopes and the equations for a road that doesn't exist? What happens to a civilization when it finally accepts its own insignificance? In the next section, we are going to look at the civilization barrier. We will move from the laws of the universe to the laws of the species. We will ask if a civilization can even survive long enough to build the ships, or whether the chain of barriers is designed to outlast every species that dreams of escaping its home world. Are you ready to see why the greatest threat to reaching the stars might be the very people who want to go? Section 8 showed us the absolute limits of the rulebook, the realization that the universe is governed by laws of causality that may never permit us to reach the stars at the speed our dreams require. But even if we assume that physics allows for a narrow path, even if we build the engines, manage the radiation, and survive the relativistic trade, we hit a wall that is not made of space-time, but of us. This is the realization that interstellar travel is not merely a technological problem, but a chronological and social one. It is the civilization barrier. We are a species that evolved to solve the problems of the next few hours, or perhaps the next few years. Yet we are attempting to master a journey that demands the stability of centuries. We are about to discover why the most dangerous threat to reaching another sun is not the distance or the energy of a pulsar. It is the internal fragility of the civilization that wants to go. To understand the weight of this barrier, we must first look at the mismatch of timelines. On Earth, we build for the next election, the next quarterly report, or at most, the next generation. Our longest-standing institutions, our governments, our religions, and our corporations rarely survive more than a few centuries without undergoing radical transformations that would make them unrecognizable to their founders. But an interstellar journey is a project that operates on a civilizational timescale. Even with the most advanced propulsion we can realistically conceive, a mission to a distant star system is a commitment of hundreds, perhaps thousands of years. And this is where the timeline of the mission becomes frightening. Humanity has rarely maintained a single institutional purpose, unchanged across anything approaching the timescale of a deep space voyage. If you launch a ship today, you're betting that the civilization on Earth will still be coherent enough to listen for your signal 4 centuries from now. You are betting that the political will won't evaporate, the funding won't be cut, and the infrastructure to receive your data won't be lost in a period of historical regression. Think about the maintenance of purpose. On Earth, if we build a bridge or a dam, it is part of a living economy. Its value is immediate, visible, and reinforced every day by the people who use it. A starship, however, is a silent investment. Once it leaves our solar system, it provides no economic return for centuries. It is a massive drain on planetary resources that offers only the abstract promise of data in the distant future. In a world of shifting priorities and resource scarcity, how long does the dream stay protected? Within 3 generations, the people on Earth will have no personal connection to the crew. The pioneers will not be family members, they will be names in a digital archive. The temptation to switch off the giant radio dishes and redirect those resources toward local crises, famines, conflicts, or planetary stabilization will eventually become overwhelming. We are an impulsive species, and the stars demand a level of collective patience that we have never demonstrated in our history. This leads to the risk of technological erasure. We imagine that progress is a straight line, always moving toward greater complexity. But history shows us that technological progress is not guaranteed to move in a constant direction. Civilizations reach peaks of achievement and then undergo periods where the knowledge required to sustain their infrastructure is lost. We see the shadows of this in our own past. After the fall of the Western Roman Empire, many of the sophisticated techniques behind large-scale infrastructure were no longer widely practiced. The aqueducts were still standing, but the specific engineering knowledge required to fix them had drifted away. On a civilizational scale, this risk is magnified for interstellar travel. If the home world experiences a great reset, a breakdown of the global supply chain, a catastrophic resource depletion, or a period of prolonged instability, the infrastructure required to maintain contact with a starship would be the first thing to vanish. The massive, high-powered arrays of the deep space network would fall into disrepair. The satellites would drift. The ship, hurtling through the dark at 10% of the speed of light, would continue to transmit its findings into a void where no one is left to hear. You aren't just losing a mission, you're witnessing the decoupling of the traveler from the species. The starship becomes a floating fossil, carrying the high-tech dreams of an era that no longer exists into a future that has forgotten its name. But the civilization barrier is not just about the people on Earth. It is about the micro-society inside the ship. As we have seen, a starship must become its own self-sustaining world. But a population of a few thousand people, isolated in a pressurized environment for centuries, is a sociological experiment with no precedent. On Earth, our societies stay stable because they are open systems. We trade ideas, we move between cultures, and we are constantly renewed by the diversity of a whole planet. But the ship is a closed system. Every social friction, every ideological shift, and every political disagreement is magnified by the absolute confinement of the hull. Imagine a generation born in year 80 of the voyage. They did not choose this mission. They were born into a metal cylinder because of a decision made by ancestors they never met. This is the risk of cultural stagnation and fragmentation of identity. What happens when a new generation decides they no longer believe in the mission's original rationale? On Earth, when a group disagrees with the prevailing culture, they can migrate or rebel. But on a starship, rebellion is a death sentence for everyone. If the technicians responsible for the life support systems stop working in protest, the entire species dies. This forces the ship toward an absolute, technocratic autocracy where dissent is a terminal threat. You are trying to preserve the human idea for 1,000 years, but in the isolation of the deep dark, that idea is subject to a drift that no manual can prevent. By the time the ship reaches the destination, the people inside may have abandoned the very science and morality they were sent to preserve. This brings us to a concept that haunts the search for extraterrestrial intelligence, the Great Filter. As we considered in the context of the Fermi paradox, the silence of the galaxy suggests a barrier that almost no civilization manages to cross. Perhaps the Great Filter is not a law of physics at all, but a recurring failure of complexity itself. We don't know whether such a filter exists, where it lies, or whether humanity has already passed it, but the possibility is disturbing. It suggests that the energy and resources required to become a multistellar species are so enormous that any civilization capable of building a starship is also capable of destroying itself. To reach for the stars, a species must possess the power of a god, but they often retain the instincts of a survivalist ape. The civilization barrier implies that the window of opportunity for interstellar travel is incredibly narrow. A species must be advanced enough to do the mathematics, but stable enough to avoid self-destruction. Think about the psychology of the backup. We tell ourselves that we must go to the stars to save humanity, to ensure that if Earth falls, a colony on another star will keep the light alive. But this is a difficult logic to sustain under scrutiny. A colony that is 10 light-years away is not a backup. It is an entirely separate, isolated event. If Earth experiences a terminal catastrophe, the colony cannot be resupplied, rescued, or supported. They are a fragment of a broken mirror. The effort required to create that fragment could be vastly greater than the effort required to preserve and fix the world we already have. The interstellar dream often acts as a civilizational distraction, a mirage that lures us into spending our limited focus on a road to nowhere, while the cradle we were meant to tend is neglected. The civilization barrier does not make interstellar travel physically impossible, but it makes it historically and socially fragile. It shows us that the stars are not our future, they are our mirror. And this leads us to the physical embodiment of this fragility, the pioneer archetype. Throughout our history, we have used fictional representations like Elias Thorne to imagine the first human to reach another sun. In our stories, we imagine him returning to Earth as a hero. But in reality, an interstellar return is an archaeological anomaly. If a traveler returned after a multi-century journey, they would be a man from the past trying to speak to a future that has moved past him. He would be carrying a warning to a world that has already survived or succumbed to the storm. He would realize that the barrier we can't escape is not the light speed or the radiation. It's the fact that time erases the context of our missions. We can build the ship, but we cannot ensure that the world we leave behind will be there to welcome us back. The civilization barrier reveals that we are a species that is allergic to the long term. We are evolved for the sprint of the next season, not the marathon of the next millennium. We look at the stars and see a destination, but we should be looking at them as a reminder of our own fragmentation. They show us that we are a collection of tribes struggling to become a unified species. They show us that our curiosity is a flame that requires a level of stability we have not yet mastered. We have spent this documentary looking for the wall around the stars, and we have found it in the fuel, the vacuum, and the clock, but we are also finding it in our own nature. We have survived the first 9 rungs of the ladder, but we have done so by realizing that the links in the chain are not just made of physics, they are made of us. But if the physics is absolute and the biology is fragile and the civilization is unstable, then why do we still feel the pull? Why did the universe give us the ability to see the stars and the intelligence to calculate their distance if the door was always meant to stay closed? There is one final layer to this mystery, one that reaches beyond the engines and the politics and into the very fabric of our perception. In the next section, we are going to look at the physics of isolation. We will explore the philosophy of the speck and the true reason why the universe might be structured to keep us apart. We will discover that the greatest gift of the stars was not the destination, but the clarity they give us about the home we have right here. Are you ready for the final, heartbreaking realization of the human odyssey? We have looked at why we can't go. Now, we must ask why we were ever allowed to dream of it. We have spent this journey climbing a ladder of increasingly brutal realities. We have seen how the vacuum destroys the machine, how the radiation shatters the cell, and how the time lag severs the soul. We have analyzed the barriers as if they were technical problems to be solved by some future genius. But as we reach the 10th rung of this ladder, we must confront a truth that is far more profound and unsettling than any engineering failure. We must ask a question that reaches into the very fabric of why anything exists at all. Why can we see the stars if the universe has made it impossible to reach them? Why did nature grant us the intelligence to calculate the distance to the nearest sun, only to ensure that the crossing would require the sacrifice of our own humanity? This is the physics of isolation. We are about to discover that the chain of barriers is not a series of accidents. It is a fundamental property of the cosmos. We will see why the universe is not a shared home, but a collection of isolated causal cells, and why the most absolute wall in the universe is not made of distance, but of the very logic of information. To understand the physics of isolation, we must first confront the lying light. When you stand outside on a clear night and look up at the stars, your eyes tell you that you are looking at a single, unified moment in time. You see a tapestry of light and assume that everything in that tapestry is there. But this is the first and greatest deception of the universe. Because of the finite speed of light, you are not looking at the universe as it is. You are looking at a historical archive. The light from the nearest star left 4 years ago. The light from the center of the galaxy left 26,000 years ago. The light from distant galaxies has been traveling for billions of years. This means that the night sky is a hall of mirrors where every object exists in a different version of the past. You are trying to find your place in a reality that has no shared now. This is the first major realization of isolation. The universe has a built-in delay that ensures every observer is perpetually out of sync with the rest of existence. This leads us to the most restrictive geometry in physics, the light cone. Imagine the history of your life as a point in space and time. From that point, a cone of light expands outward into the future. This cone represents every part of the universe that you can ever influence, and every part that can ever influence you. Anything that sits outside this cone is physically, causally, and permanently irrelevant to your existence. We call this region elsewhere. In our everyday lives, our light cones are so large compared to our movements that we feel connected to the whole world. But at the scale of the stars, the light cone becomes a cell. The physics of isolation suggests that we are trapped inside a bubble of causality that is tiny compared to the vastness of the galaxy. We can see the elsewhere through our telescopes, but the laws of physics ensure that we can never touch it. We are like prisoners in a room with a single high window. We can see the horizon, but we can never walk toward it. Think about the speed of information. Most people focus on the speed of light as a travel limit, a number on a speedometer. But the real barrier is that light speed is the maximum rate at which the universe knows itself. If a star on the other side of the galaxy explodes today, the Earth will not know about it for 26,000 years. For all intents and purposes, until that light arrives, the event has not happened in our universe. This is the causal lockdown. The universe is not a synchronized machine. It is a collection of fragments that are constantly trying to catch up to one another. The barrier we can't escape is the realization that to cross the stars is to attempt to outrun the very logic that allows cause and effect to function. If you could travel faster than light, you wouldn't just be moving fast, you would be violating the fundamental order of time. The universe prevents this not because it is mean, but because it must remain logically consistent. Isolation is the price we pay for a universe that makes sense. This brings us to the most chilling dimension of our isolation, the cosmic event horizon. We live in an expanding universe, driven by the mysterious pressure of dark energy. This means that every second, the distance between us and the furthest galaxies is growing. But here is the terrifying truth. Because the expansion is accelerating, there are regions of space that are already receding from us faster than the speed of light. Light emitted from those regions today will never reach us. They have already slipped over the horizon of our possible reality. Every day, stars that were once part of our future are crossing this line and vanishing into the absolute dark. We are living in a universe that is actively erasing itself. The physics of isolation tells us that the observable universe is a shrinking island of light in an ever-widening ocean of nothingness. We aren't just limited by our technology, we are being outrun by the fabric of reality itself. The psychological toll of this realization is the death of the interstellar dream. For centuries, we believed that the galaxy was a frontier, a place where we could spread our seeds and build a unified human empire. But the physics of isolation proves that such a structure is a physical impossibility. An empire requires a shared timeline. It requires the ability to govern, to communicate, and to respond. But if a message to a colony takes a decade to arrive, and a reply takes another decade, there is no shared now. There is no accountability. There is no collective identity. Each colony becomes its own separate event, drifting further away from its origin in language, culture, and biology. The universe has placed a security protocol on expansion, ensuring that no species can ever become a single, connected entity across the light years. We are doomed to remain planetary, not because we are weak, but because the universe is partitioned. This provides the ultimate answer to the Fermi paradox. We look at the silence of the stars and wonder why no one has called us. Perhaps it isn't because there is no one there. Perhaps it is because every intelligent species eventually reaches the same mathematical conclusion. The door is locked. They do the math on the light cone, they measure the energy of the vacuum, and they realize that the effort required to fight the universe's own structure is a waste of life. The silence of the stars might be the sound of a billion civilizations realizing that home is the only thing that actually exists. We are looking for neighbors in a universe where the laws of nature act as the ultimate social distancing protocol. We aren't hearing from the aliens because they have accepted their isolation, while we are still shouting at a wall we haven't realized is there. Think about the illusion of vision. Why did the universe give us the ability to see the galaxies if we can never reach them? Perhaps the answer is not a promise, but a mirror. The stars exist at these impossible distances to show us the value of the one place that actually works. The bigness of the universe is the context that defines our rarity. If the stars were easy to reach, they would have no value. Their distance is what makes them sacred. By making the crossing impossible, the universe forces us to look back at the Earth. It tells us that we are a localized miracle, a flicker of warmth in a cold and partitioned abyss. The barrier is not an obstacle to be overcome. It is a boundary that defines our home. We are the infants who want to leave the backyard, but the backyard is the only place in the universe where we can breathe. The physics of isolation reveals the true tragedy of the pioneer. We have used archetypes like Elias Thorne to imagine the first human to cross the void. But as we have seen, the more Thorne succeeded in his journey, the more he was erased from our world. He moved out of our light cone, out of our time stream, and eventually out of our species. He is the evidence that you cannot go to the stars without becoming a stranger to the Earth. He is a ghost from an elsewhere that we can see but never understand. The return of the pioneer is not a triumph. It is a collision between two different causalities. He has returned to find that the home he aimed for is no longer in his timeline. He is the victim of a universe that does not negotiate its rules for the sake of our curiosity. As we look at the chain of barriers, the fuel, the pressure, the radiation, the time, and the logic, we realize that they all lead to this one final point. The universe is not a playground. It is a system of sovereign cells. Each star is a cell, and each civilization is a momentary pulse of energy inside that cell. We have spent 2 hours looking for the key to the cage, only to find that the cage is the universe itself. We are the products of the very laws that keep us apart. And yet, while the physics of isolation tells us we are alone, it also tells us we are present. We are here, we are now. And in a universe where now is a rare and fragile thing, that presence is the only achievement that matters. The physics of isolation has won, not by breaking our spirit, but by defining our reality. We have survived the climb, but we have reached a peak where the air is too thin to breathe and the sky is too dark to map. We have realized that the stars are not destinations, they are the boundaries of our prison. And as we look at the chain of barriers one last time, we realize that the final link is the realization that we were never meant to leave. But even as the door closes, even as we accept the silence of the void, one final realization remains. If we are trapped on this island and the ocean is too big to cross, then how should we live? What happens to a species that finally accepts its own limitations? In our final section, we are going to look at the final verdict. We will explore the philosophy of the speck and the true reason why humanity's future is not in the stars, but with the Earth. We will discover that the greatest victory of our species was not building the starship, but understanding why we didn't need to. Are you ready for the final, heartbreaking realization of the human odyssey? The ladder is finished. Now we must look down. We have reached the summit of our isolation. For over 100 minutes, we have dismantled every hope, every loophole, and every technology that humanity has ever conceived to reach the stars. We have seen how the vacuum dissolves the machine, how the radiation shatters the cell, and how the logic of causality partitions the universe into sovereign, unreachable cells. We have stood at the edge of the physics barrier and realized that we are not the masters of space-time, but its inhabitants, locked inside a cage of light and time. But as we look down from this peak of existential dread, as we face the reality that we may never find another home among the suns, we must confront the most profound realization of the entire human odyssey. We have spent centuries looking at the distance between stars as an obstacle, a mistake of the cosmos, or a wall to be breached. But what if the distance is not an obstacle? What if it is a gift? What if the barrier we have spent this journey describing is the only reason we were ever allowed to exist in the first place? This is the philosophy of the speck. We are about to discover that our isolation is not a punishment, it is a sanctuary. To understand the value of the distance, we must first imagine a universe where the barriers didn't exist. Imagine if space was small, if the stars were as close as the planets, and if the light barrier was a permeable membrane. In such a universe, the shared now we dreamed of would be a chaotic nightmare. Every solar flare from a nearby neighbor would be a biological threat. Every supernova in the galactic disk would be an extinction event for 1,000 civilizations. The distances that we hate, those trillions of miles of absolute nothingness, act as the ultimate cosmic buffer. They provide the peace and the stability required for a biological miracle like the Earth to unfold over 4 billion years. The universe is a dangerous, radioactive furnace, but it has granted us a room of our own, separated from the fire by a distance so vast that it ensures our development was never interrupted by the tantrums of a foreign sun. We are not isolated because we are forgotten. We are isolated because we are protected. This leads to the first major realization of the final verdict, the value of the only. Throughout our history, we have been obsessed with more land, more resources, more worlds. We look at the 50 billion Earth-like planets in the Milky Way and we see a property list, a second chance for a species that is currently breaking its first home. But as the chain of barriers has shown us, there is no second chance. There is no backup drive for humanity. The physics of the vacuum ensures that any colony we build will be a separate, fragile, and temporary event. The barrier we can't escape forces us to look back at the pale blue dot with a clarity that we have spent centuries trying to avoid. It tells us that we are a localized anomaly, a flicker of warmth in a cold abyss that was never meant to be repeated. The stars do not offer an exit, they offer a perspective. They show us that our rarity is our only true currency, and that our future is not on another world, but with the one we were built for. The psychological shift of this realization is the end of the nomad. For thousands of years, humans have been a migratory species. We have always survived by moving to the next valley, the next continent, or the next frontier. We have a biological itch for the horizon, but interstellar travel is the point where the horizon finally says no. It is the point where the migratory strategy of the ape hits the fundamental constraints of the cosmos. This creates a state of civilizational maturity. We are like children who have finally realized that the backyard fence is a limit we cannot cross. And in that realization, we are forced to stop looking for an escape and start looking for a way to stay. The civilization barrier we explored in Section 9 is not a wall of death. It is an invitation to grow up. It is a demand that we become a species capable of living in a single cradle for 1,000,000 years without setting the cradle on fire. Think about the legacy of the effort. If the stars are unreachable, then was the dreaming a waste? Were the billions of dollars, the decades of physics, and the lives of people like Elias Thorne a tragic mistake? The answer is the second layer of the final verdict, the science of reflection. We built the telescopes to see the stars, but they showed us the Earth. We developed the mathematics of the warp drive to cross the void, but they showed us the stiffness of reality. Every step we took toward the stars was a step that made us understand our own world more deeply. We learned about the fragility of the heart by trying to move it to Mars. We learned about the importance of time by trying to bypass its dilation. We learned about the unity of the species by realizing that the light cone severs all connections. The starship was never a vehicle of transport. It was a vehicle of self-knowledge. It was the way the universe forced a microscopic species to understand its own context. This brings us to the philosophy of the speck, the realization that being nothing in the face of infinity is the greatest triumph of all. We have used our 3-pound brains to map the entire history of a universe that is 93 billion light-years wide. We have decoded the light of suns that died before our planet was a spark. We have stood at the edge of the abyss and asked, why, with a voice that can barely be heard past the atmosphere. The barrier is what makes that voice significant. If the universe were easy to conquer, our curiosity would be a trivial thing. But because the universe is vast, and silent, and logically guarded, our attempt to understand it is an act of cosmic rebellion. We are the dust that woke up and dared to measure the storm. The fact that we even know why the stars are unreachable is the only proof we have that we are more than just a biological accident. But as the realization of our sanctuary sets in, as we accept that the Earth is the only place in the universe where we will ever truly be home, one final question remains. What happens to the dreamers? What happens to the Voyager 1s, the Pioneer 10s, and the thousands of messages in bottles we have already tossed into the ocean? If we are never going to follow them, then what do they represent? And as the last radio signal from our most distant machines fades into the background noise of the Big Bang, what is the final message we want to leave behind? In our final section, we are going to look at the legacy of the dream. We will explore the final silence of the pioneer and the realization that some journeys are worth taking, even if they have no destination. We will see why the most beautiful thing humanity ever produced was the courage to say goodbye. Are you ready for the final, heartbreaking realization of the human odyssey? The ladder is finished. Now we must let it go. We have reached the end of the timeline. For over 2 hours, we have followed the arc of a species that dared to challenge the geometry of the universe, and we have witnessed the staggering price humanity has paid for its curiosity. We have seen the digital brains of our ships succumb to dementia, the hulls of our vessels turn into material graves, and the very stars themselves warp into strangers that no longer recognize us. We have dismantled the dream of the interstellar age, piece by piece, only to find a new kind of hope in the ruins of our ambition. But as the long journey of our exploration comes to a close, as we face the absolute finality of the chain of barriers, we must confront a truth that is far more unsettling than any engineering failure or relativistic trap. It is a truth that doesn't live in the circuits of a computer or the equations of a physicist, but in the final, cold silence of the messengers we have already sent. This is the legacy of the dream. In this final section, we are going to witness the clinical death of our farthest machines, the decoding of the final warning, and the ultimate realization that the greatest victory of the human spirit was not reaching the stars, but having the courage to look back at the Earth and finally say enough. To understand the weight of the end, we must first look at the heartbeat of Voyager 1. Launched in 1977, this car-sized probe has been our singular representative in the interstellar dark for nearly half a century. It is currently drifting more than 24 billion kilometers from home, moving through a vacuum so thorough that the probe is the only solid object for billions of miles. But Voyager's heart, a lump of decaying plutonium, is dying. Every year, its power output drops by 4 watts. One by one, the heaters are turned off. One by one, the scientific instruments go dark. We are watching the slow-motion coma of our greatest pioneer. By the year 2030, the signal will likely vanish entirely. Voyager 1 will not stop moving. It will continue to scream into the dark at 17 kilometers per second for millions of years. But it will be silent. The umbilical cord of radio contact, which we have held onto like a religious lifeline, will finally snap. Voyager will become what it was always destined to be, a message in a bottle thrown into an ocean by a civilization that knew its own island was eventually going to sink. This leads to the first major realization of the legacy, the archaeology of the record. On the side of Voyager sits the golden record, a copper disc containing the sounds of rain, the laughter of children, and the music of our greatest composers. We sent it as an invitation, a hello to the neighbors we hope to find. But as we have explored through the physics of isolation, we now know that no one is coming to find the bottle. The distances are too vast and the causal horizons are too tight. The golden record is no longer an invitation, it is an epitaph. It is a recording of a species that once believed the universe was a neighborhood. It is the evidence of a brief, flickering moment in history when we were still human enough to feel wonder and still primitive enough to feel hope. Voyager is not a bridge to the future. It is a time capsule of a past that we are already leaving behind. The psychological toll of this final silence is the end of the hero's journey. Throughout this documentary, we have used the archetype of Elias Thorne, the first human to touch another star, to imagine the cost of the crossing. In our stories, we wanted Elias to return as a hero, but as we saw in the biological mismatch, his return was a mathematical tragedy. He sat in his glass room on the moon, a translucent, stone-skinned relic, realizing that the home he aimed for had already moved past him in time. He is the physical embodiment of the barrier we can't escape. He is the proof that you cannot visit the stars without losing your place in the human family. His legacy is not a map of Proxima B, but a warning etched into his very marrow, that some journeys are not acts of expansion, but acts of chronological suicide. To go to the stars is to die to the Earth, and the universe has ensured that the two can never meet again. This brings us to the final verdict on the chain of barriers. Why did the universe build these walls? Why the fuel debt? Why the radiation siege? Why the time dilation? As we stand at the end of the ladder, the answer reveals itself not as cruelty, but as stellar sovereignty. The barriers are the universe's way of ensuring that life remains a local event. Nature has partitioned the cosmos into sovereign cells, allowing each world to develop its own history, its own beauty, and its own end, without interference from the chaos of the rest. The distance between stars is the garden wall that protected Earth for 4 billion years. If the wall were easy to climb, we would have been destroyed by the radiation of a neighbor sun or colonized by a more aggressive species long before we ever learned to speak. Our isolation is the only reason we were ever allowed to be free. The prison we have described for 2 hours is actually the fortress that kept us alive. Think about the payoff of the speck. We have spent trillions of dollars and centuries of potential trying to leave the Earth. We have dreamed of warp drives and generation ships, believing that the next world would be better than the one we have. But the legacy of the dream is the realization that Plan A was the only plan that ever mattered. We are a biological fluke, a planetary miracle that occurred in a very specific gravity, under a very specific light. The lesson of the chain is one of profound humility. It tells us that we are not the masters of the cosmos, we are its observers. Our curiosity is a flame that is meant to illuminate our own home, not to set the neighbor's house on fire. The starship was never a vehicle of transport. It was a mirror that showed us the staggering, impossible value of the pale blue dot. As the sun sets on this exploration, I want you to look at the night sky one last time. But this time, don't look at the stars as targets. Don't look at them as real estate or second chances. Look at them as the boundaries of our sanctuary. They are the beautiful, cold fires that define our place in the infinity. They are the guardians of a silence that will outlast us all. The story of humanity is not a story of a species that conquered the galaxy. It is the story of a species that wandered to the edge of the driveway, saw the depth of the ocean, and had the clarity to realize that the shore was beautiful enough. We are the infants in the dark, reaching for the lights in the ceiling, never realizing that the room we are in is the only one that will ever truly love us. The barrier we can't escape has won not by breaking our spirit, but by defining our purpose. We have survived the climb, but we have reached a peak where we can finally see the truth. The stars are waiting, but the Earth is breathing. We are home. And as the last radio signal from Voyager 1 eventually fades into the background noise of the universe, as our most distant messenger finally goes quiet in the dark, we can look up at the night sky and know the final verdict. We were never meant to reach the stars, because we were meant to be the ones who saw them. And in a universe of infinite scale and absolute isolation, being the only ones who can see the light is the greatest triumph of all. The airlock is closed, the engines are silent, the Pioneer is at rest. The ladder is finished, and as we look down from the height of our ambition, we see the Earth for what it really is. A tiny, fragile spark in a black ocean, a noisy room in a silent house, and the only place in the entire universe where you will ever truly find your way back. Thank you for joining me on this 18,000-word journey through the heart of our isolation. If this exploration of the limits of our species has changed the way you look at the stars and the world beneath your feet, please take a moment to like the video and subscribe to the channel. Your support allows us to continue building these cinematic bridges into the deepest mysteries of our existence. And the next time you feel the pull of the night sky, just remember, the stars are far, but the grass is near. Keep looking up, but never forget to look back. Good night, and may your path always lead you home, even when the stars say there is no road back.